Thanks so much for your kind introduction. So today I'll give a talk, zeolite fixed metal nanoparticle as efficient heterogeneous catalyst. You know, metal nanoparticle always shows very high activity, also but no selectivity. Also, the metal nanoparticle easy for sintering. For the metal sintering means the small crystal became a large one. On the other hand, zeolite crystal always gives excellent selectivity, also very high stability, but it's difficult to introduce metal nanoparticles. The question is possible introduce the selectivity and the stability of zeolite framework to metal-based catalyst. The question to student, also myself. Our designed catalyst just here, just another particle fixed with like a zeolite framework, where the macropore offer the selectivity. Zeolite framework shows very high stability, and the metal nanoparticle shows very high activity together. So in the literature, there are already report nanoparticle in the macropores. But in this case, you know, nanoparticle easy to make the movement, so still sintering. In this case, the macropore usually less than 0.8 nanometer. But industrial catalyst always 2 to 5 nanometer. It's difficult to introduce a zeolite crystal. So how to avoid the sintering? Could 2 to 5 nanometer nanoparticle combine with zeolite framework? This is always to the student. So right now we have new idea. So the nanoparticle, the diameter always larger than the macropore size. In this case, fixed with zeolite framework. So in this case, the nanoparticle cannot make any movement. But the question, how to prepare? I will use a new method. This method is a seed direct synthesis. So in the beginning, we use a zeolite seed, and then to make the seed direct crystallization, finally, all the metal nanoparticle will be fixed with zeolite crystal. So nanoparticle always inside of zeolite crystal. Also, we use the other method. The other method is use the solvent-free synthesis using the method. So all we get dry material just in situ crystallization, solvent-free crystallization. Finally, all the nanoparticle fixed inside of zeolite crystals. So here you can see this tomography, all the nanoparticle fixed with zeolite crystal. So we also asked the world top professor, you can also find the nanoparticle fixed with zeolite just inside of zeolite crystals. Also from TM, you can find this crystal fixed with zeolite crystal. This is nanoparticle fixed with crystal. So the size of nanoparticle also easy to control, from 1 to 3 nanometer, even to 5 to 8 nanometer, even 10 different size we can control. So after get this material, so we try to prepare a reaction of a metal nanoparticle-based catalyst shows is efficiently the catalyst. So here today I show the 3 parts for the efficient catalyst. The first one, try the shape selectivity and high stability of zeolite to give the metal nanoparticle catalyst. Here I show the 3 examples. The part 2, I show you the functionalized group, modified zeolite to give like a zeolite nanoparticle-based catalyst. Here I show you 2 examples. The part 3 shows you the just physical meeting of functionalized zeolite or material with classical catalyst. Here also shows the 2+. And first show you the part 1, shape selectivity and high stability of zeolite framework to give the metal nanoparticle catalyst. The first one show you that shape selective absorption of zeolite enhance the product selectivity in hydrogenation of natural iron. So this hydrogenation, the problem, just like the low selectivity, also aggregation of nanoparticles. So why the low product selectivity, which due to the low absorption selectivity between natural group and palladium nanoparticles. So absorption type, just phase absorption gives a byproduct, but the linear absorption always gives our desirable product. But how to enhance the selectivity for linear absorption? This is the question. So after the new idea, use zeolite Magpul. Zeolite Magpul just gives the one choice, shift selective just gives linear absorption. So all the linear absorption, then we the substrate just linearly into the zeolite framework pour to get our desirable product. This just use the zeolite Magpul shape selectivity. So this is our sample, palladium fixed with beta zeolite. On the surface, you cannot find any nanoparticle, but inside, cut by the diamond knife, you can find the palladium nanoparticles. So here shows the catalytic performance. So only our new catalyst shows 100 conversion, 100 selectivity for our desirable product. But others always get the byproduct. For the other substrate, also we show the very high selectivity, very high activity. The second two examples show you the selective conversion from furfural into Feng by adjusting molecular diffusion. You know, this hydrogenation also there are many different products, but our desirable product just Feng always gets low, very low selectivity. Why? Due to complex reaction mechanism, there's just a little selective for Feng. We found the quite different product have quite different diffusion rate in zeolite crystal. So also from infrared or the theoretical simulation, we found that Feng is very fast diffusion. So we gave a new idea, probably faster desorption shows higher selectivity for the product. Then we prepare the catalyst, that's nanoparticle fixed with zeolite, S1 zeolite. So here, just like a nanoparticle fixed with zeolite. Then you can compare the selectivity. For the supported catalyst, shows the selectivity just 5.6% for the selectivity. But fixed zeolite shows the selectivity even 98%, very high selectivity. But why? This is our explain. For the supported catalyst, after hydrogenation, we get alcohol. But fixed zeolite is different. Even formed alcohol cannot diffuse out. Have to continue to for hydrogenation. Finally, get Feng to quick, faster diffusion. We get the Feng, the product. So the third example, I show you citrine-resistant metal catalyst. You know, here, like this is a different noble metal, not a particle. We just fix with zeolite. For the supported, you can, in the beginning, very high conversion, so react with time, so activity reduced. Calcination, so activity further reduced. But for the fixed catalyst, it's very stable, even lost activity a little, but after the calcination, so activity return back. But why? We did the TM. You found that the used catalyst already become a large particle during nanoparticle citrine. But right now, for the nanoparticle phase with zeolite, it's very stable, still very small nanoparticle. It's almost the same as before. Not only for this reaction, but also for the other reaction. For this one, but supported quickly reduce activity. But the run-on fixed even reduce activity a little, but after castration to return back. The run-on, the fixed the catalyst is much more stable than the others. Also, we know the challenge for the syngas to ethanol, very important. Also, there are the aggregation of rhodium nanoparticle, and also give very low productivity. But how to solve this problem? We also use like nanoparticle faced with zeolite crystal. Also, for formation of more active intermediate, this intermediate just rhodium delta plus with XIAO. Our preparation, similar before, so nanoparticle, rhodium nanoparticle fixed with zeolite crystal. You found this reaction, CO to hydrogen to ethanol. For supported, you found that just quickly lost activity. Yeah, in the beginning, not so high, but after 50 hours of lost activity. But right now, just fixed with zeolite crystal, in the beginning, very high activity, even for the over the 225 hours, still very active, also very stable. For the spent catalyst, used catalyst from TM, you found still the very small nanoparticle. No change, any change for the nanoparticles before and after the reaction. But why this is so active? We found the intermediate, like this species, very stable. So here, almost no change before and after. The number 4, I show you just a stable and active catalyst for dry reforming of CO2 with methane. This reaction is very important right now, especially for currently for the reduced carbon dioxide. For this reaction, usually it's 1 CO with 1 methane to CO. For this reaction, the major challenge is just cold formation, also the short catalytic lifetime. But how to solve this problem? So also, right now here, active site fixed with zeolite crystal, enhancing the stability. The design of catalyst, we use the nickel, even nickel cobalt fixed with zeolite crystal. Here, I show you the performance. So here, just supported, this supported 75, so quickly lost activity. Supported by the silica, also lost activity. But here, just fixed with zeolite, very stable. Even 100-hour reaction, still very stable. Similar for this one, you can find here this methane conversion, CO2 conversion, all just here, the nanoparticle fixed with zeolite, very stable. Here, I show you the live. So here, even 200 hours still just a little reduction for the activity and the selectivity. So after the fixed active site fixed with zeolite crystal, stable and cold resistance. Also for the here, cat life, here even the 1,000 hours still very active, even lost activity, but after regeneration, activity return back due to no change for the nickel nanoparticle size. Not only the dry reforming, even for the super dry reforming. There are 8 years ago, American professor reported the super dry reforming. Here, the X about 2.2. The 1 methane react with about 2 CO2 to form 3 CO. But where the S about 2.2. So the question to students is possible to get this value higher than 2.2? If so, it should be the hydrogen in the methane should efficiently react with the CO2. For this reaction, hydrogen spillover is very important. Hydrogen spillover is favorable for CO2 hydrogenation. So we design catalysts with very strong hydrogen spillover. So hydrogen spillover, we use like a proton 75, just a nickel nanoparticle faced with this zeolite. So here is our preparation. So here, nickel nanoparticle fixed with zeolite. This kind of catalyst shows very strong hydrogen spiral ability. How to test? We use this one, a color change. Right now, we use a new nickel nanoparticle phase with a hydrogen form, then 5 catalyst. Here, the SU value almost 3. This is very high. The one machine with almost 3 CO2 to form pure 4 CO. Here, hydrogen also water almost 0. So also I show you the stability. The 3,000 minutes still is very stable. So here, this catalyst, long catalyst life, very high active, highly active, also high reduction value. So this reaction also important, for the many initial gas field, just like a rich carbon dioxide. Some cases even higher than 80%. But for the commercial use of natural gas, carbon dioxide always should be less than 2%, which requiring separation of carbon dioxide with natural gas, which is really energy consuming. But here, I give the new route, we can get the pure CO even from the carbon-rich natural gas. So which is very, very important. Then the first part to show you almost just like 17 minutes. So part 2 show you functionalized group modified zeolite to metal nanoparticle-based catalyst. The first one, in part 2, I show you construction of molecular fins metal nanoparticle by hydrophobic sealing for conversion of methane into methanol. It's well known that the methane with hydrogen peroxide to methanol can occur at room temperature. But hydrogen peroxide is really costly. Also, we know hydrogen with oxygen to hydrogen peroxide can react at a low temperature, even the room temperature. But it's difficult for the reaction methane, hydrogen, oxygen together to form methanol. But why? We found that the major challenge just hydrogen peroxide diffusion very fast. No way to make the reaction between the hydrogen peroxide with methane. So the question is possible to construct molecular fins to handle the diffusion of hydrogen peroxide. We try to make a new idea. If this is a picture, I'll get a new idea. It's possible to take a molecular fins. Molecular fins design just like this catalyst coated the monolayer, hydrophobic monolayer, like sealing. So here I give you the molecular fins enriched hydrogen peroxide. So from NMR, we can confirm these molecular fins. Then we try to synthesize hydrogen peroxide. You found without molecular phase, all the hydrogen peroxide just in the liquid phase. But just with like molecular phase, large amount of hydrogen peroxide just in the zeolite crystal, inside of zeolite crystal. For the methane oxidation, get a similar thing, just molecular phase enrich hydrogen peroxide inside of zeolite crystal. Right now, we construct the molecular phase. So here, hydrogen, oxygen, and methane pass through the molecular phase inside. After the formation of hydrogen peroxide continually react with methane to form methanol. After the formation methanol, so easily pass through the molecular phase to get a methanol product. Use this way, you can compare the activity. Without the molecular phase, almost inactive. But just give the construction, after construction of molecular phase, conversion very high, selectivity over 90%. Conversion higher than 17%. How about stability? Recycle 10 times, almost no change. The second example, I show you the beta zeolite with a rich solenoidness reverse ostward ripening for durable copper nanoparticles. You know, for this reaction, also copper nanoparticle very potent is also one of the key catalysts for hydrogenation. Just 2 years ago, even China market, the production of need at least 5,000 ton copper nanoparticle catalyst. But the copper nanoparticle easy for the sintering, especially under the methanol condition, then reducing the activity. The question is possible to reverse oswald ripening for copper nanoparticle? Inspired by our synthesis of zeolite, we found diameter is strongly dependent on the nuclei concentration. Always we found more nuclei, smaller crystals of zeolite. So we think the similar thing for the copper sintering, also process of growth of crystals. Therefore, it's possible to have more copper nuclei on the catalyst surface. So then we get a new idea. We want to get a more strong interaction size for the formation of more copper nuclei. The method just to prepare zeolite with solenoidness to strongly interact with the copper species. But how to generate the strong active site? So we get the de-elimination, we get the solenoidness. So from infrared, we get this strong peak. For the isolated, just here the peak. So this net structure. So here, this structure easily, strongly interact with the copper species. So if we use the like this rich zeolite to reverse the copper ripening. So here, this beginning. So here, just under this support, after the methanol training, 70 hours at almost 200 degrees C, so many copper species became very smaller. But after 190-hour treatment, we cannot find any larger copper species. Just a bigger copper nanoparticle became very small one. Also, we use XRD confirm this phenomenon. In the beginning, the large particle you can find copper X-ray diffraction. But after the 190-hour, this peak disappears, confirming the copper reversed ripening. But why? The reason. The reason, just like methanol-induced copper species, we use the TOF mass, also use other technique to confirm there are many different copper intermediate. This intermediate also can control the pressure and also gas phase. But only methanol easy to form the copper species. CO and hydrogen doesn't work for form this kind of species copper intermediate. This copper intermediate migrates to large one just to give the ripening. But to move to the next place, just reverse the ripening. So right now, also we use a theoretical simulation. We get the similar conclusion. Also from cyclotron, confirm this phenomenon. So right now, we can get the efficient copper nanoparticle support beta zeolite. So the methanol treatment can from a big one to become a smaller one. So right now, the copper nanoparticle can get reversible. We can changing the regeneration, can continue to recycle, continue to regeneration, so almost no loss for the activity for a long time. So here you can show the activity and the selectivity, very high activity, also very high selectivity. So here, almost 100% conversion, 99% for selectivity. So here, reversing the ripening solves the difficulty for nanoparticle in industrial process. We would like to say this process already commercialized in China. So this, the new way can solve the problem for ripening for the carbon nanoparticle. Even for the 1 atmosphere, still very good. So still very stable, the yield over 90%. I'll show you some of the zeolite phase nanoparticle is very good, but the preparation looks complex. So it's possible to prepare the zeolite-based zeolite nanoparticle composite by a simple method. Always think about this. We want to get a new idea. Of course, the simplest method just like a physical mixture. Then we try. I show you the physical mixing of functional light zeolite or porous material with classical nanoparticle catalyst. I also show you 2 examples. The first example, just a physical mixing of zeolite with iron-based nanoparticle for conversion of syngas to light olefin. FT synthesis is very important. Particularly right now, is for the carbon neutrality is very important because syngas is easy to get the biomass, also from a conversion of CO2. For this reaction, CO and hydrogen to olefin, for this reaction in China did many excellent work. The first work from the Professor Xin Bao use the oxide and zeolite together. In this case, gets a very high olefin yield. But in this case, the temperature higher. On the other hand, use the classical catalyst from the Professor Yu Hansun in the Shanghai. The temperature was just over 250, low cost, but lower olefin yield. So our new idea is possible to enhance the yield over classical catalyst. So we try to get a new way. For this reaction, CO with hydrogen to give the olefin and water and carbon dioxide. Our idea just addition of a promoter for absorption of olefin. If remove the olefin for the product, we are shifting the reaction balance. So therefore, we just searching for the olefin adsorbents. Quickly, we found pure silica, S1 zeolite with a rich OH group are favorable for absorption of olefin. Then we take physical mixture of this S1 with a rich OH group with a classical catalyst together. You can, before the fixing, just like a classical self, show the activity not so high, just conversion about 20%. But just the physical mixing gives a conversion almost in at least 4 times, increasing the conversion higher than 80%. So here also shows the stability, also activity, also very high. So just physical mixing significantly enhance the yield for the light olefin. Also confirmed by the infrared for the just the physical mixing. So here is a similar intensity, but after 12 minutes, so here the physical mixing is just a much weaker intensity. So here we found the desorption rate of propylene on the classical on the physical mixing was much higher than on the classical, so shifting the reaction balance. Also, we introduced light olefin into the reaction system. For the classical catalyst, introduce the olefin, so activity quickly reduced. But here, even introduce olefin, light olefin, or just a little reduction for the yield. So here also confirmed of the catalyst favorable for desorption of ethylene on the catalyst. From a theoretical simulation, also get the very similar phenomena. So just classical self, you can find the number of the olefin is higher, but just because the physical missing, so quick the light olefin number quickly reduced. So I show you just shifting the olefin. On the other hand, I also want to tell the student try to remove the water byproduct. So also we think the faster mass transfer of water product probably also shift the reaction balance. The next question, what kind of material for faster mass transfer of water? Of course, already reported this superhydrophobic promoter. What kind of superhydrophobic promoter? So you can see the water mass transfer very fast. But conventionally, this here is the conventional. So the water not easy to make a movement. So here the continuum angle higher than 156 degrees. So this material also prepared out the lab. 18 years ago, we gave the name PDVB. So right now, we just give the physical missing hydrophobic promoter enhance performance of FTO. So the new preparation of a new catalyst, just physical missing, just like PDVB with classical catalyst. So here, the classical catalyst, the cobalt COMN carbide. So here, usually the classical catalyst, the conversion about 30, selectivity for light olefin 60. But right now, just take a physical missing. So here, conversion about 63, selectivity or higher than 70. So here, just addition of PDVB conversion double. No any loss for the others. But in the starting source containing a little carbon dioxide, even carbon dioxide selectivity can lower to 23%, which is also good for carbon neutrality. This reaction always very stable. So here, selectivity higher than 70, even the 120 hours. Also conversion, CO conversion is also very high. The reaction temperature only 250. Even introduce water for the classical activity, classical catalyst to quickly reduce activity. But right now, it doesn't matter if you introduce water because superhydrophobic promoter, so the mass transfer very fast. So why you give the plane? So you introduce hydrophobic, hydrophilic surface, so it's different. So you introduce hydrophobic, so the diffusion rate faster. Then, so here there are the difference for the pressure. So this is a catalyst surface, the water so diffuse this side, which due to the Bologna effect. Bologna effect is very popular in the nature. Like, so here the diffusion rate is different, so we get the air current lifting. This is also similar. So the Bologna effect usually just a large scale, but here I just show you just like the Bologna effect, just a very small size. So from a theoretical simulation, also we get very confirmed similar thing. So right now just 35 minutes. So I would like to conclude my research talk. So here are just fixing noble metal nanoparticle in zeolite has many advantages of both high activity and excellent stability and shape selectivity. The physical mixing of functionalized zeolite with classical catalyst exhibit excellent property. There are many, here just an example. This kind of example provide a good opportunity for design efficient metal nanoparticle catalyst. So zeolite-based catalysts have very good future. So our research, beginning my research in the 30 years ago, was with our supervisor Bruce Gates. But right now, also get many professor support. Yeah, like even many different plots. Due to limited time, I cannot say more. So this is our group. Right now, the 5 young professors together. This is our group. Thank you very much for your attention.